Hello everybody, in this video we are going to be solving the following problem that asks us to test for Stokes' theorem for the following function using this triangular shaded area that I have depicted here. The way we're going to do this is we are going to independently solve each side of the equation and then we're going to compare the results, and in theory they should be equal. So the first thing we need to do is identify what the curl of V is, and I have put here the formula so that it's easy for us to just see. Okay, we got the partial derivative of the z term in respect to y, but there's no y variable here, so it's just going to be 0. And then we got the partial derivative of the y term in respect to z, so that would be just 2y. And then we just continue doing this for the other terms. The partial derivative of the x component in respect to z is also 0. Then the z component in respect to x is 3z. And finally, we got the y component in respect to x, just 0. And the x component in respect to y, that would be just x. So we get that the curl of V is equal to minus 2y x component minus 3z in the y direction minus x in the z direction. Alright, the next thing we need to look for is what this dA means. dA is an infinitesimal area element that is corresponding to our area here. Since our area is only depending on the z and y plane, then we're going to have dc dy, and remember that the direction of an area is perpendicular to it, so in this case it would be pointing in the x direction. Once we dot product the curl with this area element, we are only combining the like elements, so our x direction and our x direction here are going to combine, and since we don't have any y or z components in our dA, these terms here are not going to matter. That means that this entire term inside the integral is just minus 2y x times dc dy x. The x times the x, they just unit vectors, so it becomes 1, and the entire result is minus 2y dz dy. So this is what's going to be inside our surface integral here, and we're just going to go ahead and solve it. We're going to set it up. Let me use this. I'm going to put the minus outside just for simplification. 2y dz dy. Now we're going to have to find the boundary conditions of our integral. In this case it's easy because we can see that y just goes from 0 to 2. However, in the z component we have a y dependency because z goes from 0 all the way up to this line, which has the equation 2 minus y. That means that in our integral, which is a double integral by the way, we're going to have to solve for the z part first. So I'm going to rewrite it as minus, like this, 2y, and instead of having, oh never mind, we just go dc dy, and our z we know that it goes from 0 to 2 minus y, and our y goes from 0 to 2. So this is just a very easy integral. We're gonna solve for the inner part first. We know that this is equals to y squared from 0 to 2 minus y dy, which is equal to 2 minus y squared dy, and this is equals to 4 minus 4y plus y squared dy, and solving that you get minus 4y minus 2y squared plus 3y, sorry, y cubed over 3. Yeah. And this is going to go from 0 to 2. The 0 term doesn't matter, so we're just going to have to plug in 2 for every y in here. So we got 4 times 2 is 8, minus 2 times 2 times 2 is 8, plus 2 cubed is 8 over 3. We see that these two cancel out, and we have the minus here still. So that would be minus 8 over 3. This is our result for the left side of the equation. And now what we're going to do is solve for the right side and see if we get the exact same result, which, spoiler alert, we do. Okay, so in this right side, which I'm going to start here in blue, right side, we have our vector function, and we have an infinitesimal path element, which in Cartesian coordinates we know that it's just dx plus dy plus dc, each corresponding to its own unit vector direction. So what we have here is actually just a dot product. We're just going to dot product this with our vector function. So we combine the elements corresponding to each direction, which means that our generalized dot product is just xy dx plus 2yz dy plus 3cx dz. Now, in order to solve this line integral, we need to also find what paths we are going to be using. And my strategy will be to separate this entire loop into 3 sections. The first one being that one, the second one going from here to here, and finally from here to here. So let's start with path 1. Let's see what we get. We need to now define the boundary conditions of each variable in this path. So we see that x just stays 0. We don't have x involvement in these paths. Then y goes from 0 to 2, and z just stays 0 as well. Plugging this into our equation, we get this term cancelling because x equals 0, this term cancelling because z equals 0, and both z and x equals 0 here. Therefore, our dot product just goes to 0. And this means that the entire integral is also going to go to 0, meaning that this doesn't contribute at all to our result. So now let's look at path number 2. Again, we don't have any x involvement here. Our y goes from 2 to 0, and we have that our z goes from 0 to 2 minus y again. Alright, so we're gonna see what cancels in our function. X equals 0, so this term goes away. This term goes away too because x equals 0. So the only thing we are left with is the middle term, 2yz dy. However, knowing that z equals 2 minus y, we can just put everything in terms of y, like this, which turns into 4y minus 2y squared dy. And this is what we are going to be plugging into our integral. So we're going to have this 4y minus 2y squared dy, knowing that y goes from 2 to 0, so we're going to invert that order. We're going to put it negative in front, going from 0 to 2. Now again, this is just an easy integral. We get y squared over 2, so just 2y squared minus 2y cubed over 3 from 0 to 2. That would be just plugging in the 2 for every y, so we get here 8 minus 2 times 8 is 16 over 3, and then we can just distribute the minus, so minus 8 plus 16 over 3. Just for doing this quickly, I'm going to turn this 8 into 24 over 3 plus 16 over 3, and we can see that minus 24 plus 16 is just minus 8 over 3. Okay, finally we get the third component, or the third path in our line integral, which has no x involvement. We get that z goes from 2 to 0, and y is also not involved in this side. So once we put these numbers here, this term goes away because x equals 0, this term goes away because y equals 0, and here x equals 0 would also eliminate it. So our dot product is 0, meaning that the integral does not contribute anything to the result, which is what we expect, since this is already the result we were looking for. Goes minus 8 over 3. So combining our results from the left side, we get minus 8 over 3, and in the right side we also get minus 8 over 3, which means that we have tested Stokes' theorem to be actually working.